Yeah. Okay. So actually, I was at the top of this thing. Okay, so let's see what. I thought I had that thing open. I did at one point. Oh, I do. What is it doing? This thing is really slow. Let's see if it'll sound. So we talked about Bernoulli's. We were on Bernoulli's, but I need to find a couple of problems that are kind of, I guess I could find them in the book, but I can also, there's some standard problems. But it would be good to have the picture. But, I think I'll just wing it because the problems are all standard. I mean, there's not really anything fancy about them. So let's look at a situation. Now, this is going to be weird. Like a situation in which you you flow. Here's a river flowing to the right, and it meets this spot. It flies under it, and it's heading downstream down here. So the question is, let's say this is 10 feet deep and moving, how about 20 feet per second? So it's moving really fast. The water's moving really fast to the right. It hits this kind of spillway or sluice gate or something like that, kind of similar to the spillway over there. Then the water rushes down through here and out down here. So the question is, what's the height and what's the velocity? So the way you can do this is tag yourself to two locations, 1 and 2. And what you can do is you can basically say P1 plus gamma Z1. Now, it kind of depends on the way you look at this, because in one way, a civil engineer would divide by gamma. A mechanical engineer, which is who I am, they're not going to divide by gamma. And so, what's going on here? Hang on a second. What is happening here? Hang on. Let me see if I can call them back real quick. If you don't mind. Hey. Well, so I was in class. I accidentally hit your thing to dial you. But how are you doing? Oh, okay. Well, I'll let you go and I'll get back to class there. Okay. All right. Yeah, that's good. I just accidentally hit the button. Okay, I'm gonna go. Matthew and I may go to eat in a bit. So, okay. Yeah, just call me. Okay, bye. Okay, sorry about that. I just want to make sure everything's right. So a mechanical might write it like this. Okay, but a civil will kind of write it like this. And essentially, they're focusing on the units. Here, the units are pounds per square foot, say, and here the units are just feet. So we're going to pretend to be a civil engineer for a minute. Okay, and so we're going to write between 1 and 2. And what we'll do is we'll go ahead. I know this may sound weird, but I like to make the table every single time. Even though it sounds weird because there's only 2 locations, but at least I can sort of look at what I know. Here, I know the height at 1 is 10 feet because I'm going to use this as the datum. And I know the height here is h feet. So it's a certain height there, but I don't know what that is. I know back here at 1, it's 20 feet per second. And at 2, I don't know it. So I'm just going to say V2. And then I know the pressure of both of these locations is atmospheric. So the reason I do that is because in the rush, now I've heard several of my students in the past who have taken the PE exam basically said this chart really helped them a lot, because when you're faced with a funny problem on the exam or PE or FE or whatever, and you're looking at it, sometimes if you just make this chart, you can identify what your unknowns are. So you can identify that first, I know everything here, so I can determine the energy state from this. But here, I don't know, I don't have one thing that's unknown, I have two. So that tells me already I've got to come up with another equation. But it turns out that, it's the mass flow equation. So, let's see, was that it? Yeah. So in other words, A1 V1 is equal to A2 V2, and that gives me the second equation that I can fill in here. So let's take care of the Bernoullis first. And so what I got now, the other thing is I can identify, I'm taking everything out of 1 and putting it right there. So the pressure is going to be 0. The elevation is 10, and the velocity is 20. So 20 squared over 2, and I'm in feet per second, so I've got to use 32.2. And that's, from that, I got my constant. I can figure this out. As a matter of fact, yeah, hang on. Let me just go ahead and see. I can just zoom back, and this will be 16.21. That's good enough. That's as many digits as I want. And now I can take this row and put in here. So immediately this is the case. The second one being H, and the third one being just V2 squared over 2 times 32.2. So I'm sitting there and I'm like, okay, now I've got on my right, I've got H. Let me just V2 squared over 2 times 32 plus what? So what is that? 64.4. So I've got an equation here. But I'm kind of stuck. Except that I realize up here, without too much fanfare, I can drag it down. I can realize the height back here was 10 feet. So we can do this for one. So A1 V1 is equal to A2 V2. Well, A2 is H, the height, so the area here, let's assume that this is 1 unit into the page and 1 unit into the page back here. So in other words, from a top view, the river doesn't spread out like this. The river kind of just basically goes the same, so here's my gate. This is the sluice gate right here. And the water's flowing, but it doesn't widen out. And since it doesn't widen out, I can just use the depth as the area. So back here it was 10, the velocity was 20, and over here it was this. So now I've got an issue. I got to choose which one I want to solve. Okay, so I can insert this back in here. I can solve for either H or V, and then work it out. But I think what I would prefer to do right now is solve for H. So what I want to do with this equation is take V2 is equal to, I think that's still 200 over H, and I'd like to insert it right there. 16.2, not 1, 2, 1, 1 equals to h plus 200 squared over, so I'm putting this v2 in here, squaring it and copying it down. It doesn't look like a square, does it? Now it does. Over 64.4 h squared. So, just out of curiosity, I'm going to see if this thing will just solve that. I would doubt it, but it will be interesting to see. Uh-oh, oops, we can't solve this. Okay, so what we'll do, we'll take this box, we'll put this equation in a box. We're going to multiply everything in here times h squared. And what we're going to get is 16.211 h squared. And then, let's see, do I want to move everything to the left or right? Well, I'll just do this. H to the third plus, let's see, what's 200 squared over 64.4? That is actually 621, so I'll just erase that. 621.118. So now I'm going to see if it'll solve that. I bet it won't, but it might, but I doubt it. Oh, a graph? What the heck is that? Explore the graph. It's like weird looking. What? Oh, this is funny looking. The graph is, it's coming up. I'm gonna put things together. Okay, so I'm gonna just work this out in one more state. I'm gonna drop down and rewrite the equation. H3 minus 16.211 H2 plus 621.118. Now, sorry, equals 0. Now, I don't think it's going to do any better there than it will anywhere else. That's really weird. I don't know what. You know what? I don't think it actually got the right equation out of it. It just put the equation that said graph. Let me try this one. I don't think it understood what I was actually trying to say there. Oops, can't solve it. Okay. So what I'm going to do is try to come up with a solution. So I am going to first, now this comes from me kind of knowing what's going on. But I'm going to put in h equal 10 and see what happens to this side. So what I'm going to do is I'm going to put in 10 to the third minus 16.221 times 10 squared. And I'm going to try to calculate that. Let's see what that would give me. And that's going to give me equal to minus 622.1. Now, why did I know that? Okay, so one of the solutions is going to be h is equal to 10. Okay, and I'll tell you why I know that's the so one solution is h is equal to 10. Okay, so how do I take this h equal to 10 and figure out the rest of this? So if you remember, okay, hang on for me. H minus 10 times, okay, this is cubic. So I'm going to say A h squared plus B h plus C has got to be equal to, and I don't have anything to do except do that. Okay, the reason h, one of the solutions is h is 10 is not completely intuitive unless you've worked the problem before. And one solution would be the water would come back up and just continue flowing to the right. So in other words, and this is one common situation that can happen on these. In other words, and this is also the behavior of something that is, there are three classifications of differential equations: hyperbolic, parabolic, and elliptic. And that means anywhere it can affect everyone. Structures is all elliptic. What that means is if I put, believe it or not, if I put a force, if I drop a weight on this table that's not on that table before, there's a new stress on this table, but it is also in every part of this building. So this point affects every other point. It's elliptic. Hyperbolic is more like a duck is flowing down, here you go. A boat's going this way. A duck is sitting there. This boat is going by. This duck has no effect. This boat has no effect on this duck until he passes him, and then the wave hits him. This is an hyperbolic behavior. It's a wave equation. It turns out that fluids falls into all three categories. It can be wave equation, it can be parabolic, and it can be elliptic. So what I mean by that, let's say you had this, and the water's flowing, and suddenly nobody discussed what happened down here. But let's say suddenly I put a wall up here that was like this. So what do you think would happen? Well, the water has to climb to go over that wall. So suddenly what will happen over time is that'll be one. So for a few seconds, you might see this. A few seconds later, you might see this. And then what will happen is eventually it'll fill up to the point where it's completely like that. And then the flow here is 20 feet per second. Flow down here is 20 feet per second. This is 10, and this is 10. And essentially, it's as if this thing was just creating a problem right in here, making the velocity go faster and then back like that. So the fact of the matter is, you put something down here in the flow, and it had an effect back this direction. But it took time for that to occur. So one solution is 10. In other words, the solution could be that is exactly what happens. It's 20 feet per second. It's 10 here. It's 10 here. Guess what? That point and that point have exactly the same energy. Continuity is satisfied, so everything is satisfied. But there is another solution, and the other solution is it continues and gets smaller. So let's see if we can back out and find that solution. So from this, what I'm going to do is I'm going to go after the A, the B, and the C, and once I got those, then I can use the quadratic equation and try to find this. So what I'll do is I'll take off and hit the H against the H, or the H against the H squared. There's only one cubic term, and that's that one. Therefore, this is 1. So H squared gives me that term. Now, I'm looking for everything that is quadratic. That is, this term times that one, and this term times that one. That'll give me minus 10h squared, and this will give me plus b h squared, and that's got to be equal to minus 16.211. So I believe, if I'm right, that's got to be minus 6.211. Now, maybe I'm wrong, but if I am, correct me, because my brain is not working very well today. Now I'm looking for the H's, everywhere an H occurs. There, and there. So I get CH minus 6.211H, and that has to equal 0 because there is no H back here. So that means C has to be, hang on, And I think I'm, hang on. Wait a minute. Minus. Wait. It's got to be plus, right? It's got to be plus. 6211. 0.211. Now, did I satisfy the constant term? This times this. Is that equal that? Uh-oh. But, I haven't used the constant term. Wait a minute. Was that supposed to be a minus or a plus? Was that supposed to be a minus? That might have been supposed to. I forgot already. I can't rewind the video because I'm in the middle of it. Poop. Okay, let me recheck this. I had a constant, right? I'm trying to get the 0 out of there. So I'm taking the h, multiplying it times the c. C times h. Taking this one, and multiplying times that one. Minus 10 times that equals 0. So it is a minus. Okay. Somehow, this is weird because I just did this and my short-term memory is just fried right now. So I do not know why my short-term memory is fried. So if I multiply this times this, I do in fact get that. So this is the equation. So this, and I did this in a weird way, it's the same thing as that. So now I just need to find that. Now it should be able to find this for me. 6.211 h minus 6.211. Is it supposed to be 62?
10 times that should be 6.1.
Oh God, did I do that wrong? Okay, let me go back and let me try to make sure I got this right. Oh, this is hilarious. Okay. C times H, and then 10 times that. Okay. That times that is plus 62.1. You are correct. Oh my gosh. Okay. Okay. You are correct. Man, my short-term memory is gone. I must be hungry. H squared minus 6.211 h minus 62.11. Let's see if it can solve this one. It's got to be able to solve this. If it can't solve this, this is terrible. Oh, it did. Okay. It recognized that it was a quad. So it's got two solutions. One minus 0.5365, and the other one is 11.576. Now, I don't trust anything. So first of all, that's not possible. So the second of all, is h equal 11.57 reasonable? Yeah, it is. That doesn't, that's very bothersome. So what did I do wrong? And is there anything wrong with this? And there may not be, but let's take this. So what we're going to do is we're going to take this. We're going to go back and make sure that Bernoulli's is satisfied and continuity is satisfied. So what I'm going to do, I'm going to go back and do A1, B1 equals A2, B2. Okay, now the key is I haven't found the V yet. So I got A1 with dots on the left. So this total becomes 200. This becomes 11.576 times V2. So this means V2 has got to be, okay, maybe I better do this with a calculator. Let's see, 200 11.576. I get 17.277. Okay, now what I'm going to do. So here's what I did. I went in, I found this, right? I'm asking the question, is it correct or not? Is this kind of reasonable? Okay. So I'm going to take this V2. I'm going to go right back to here. Hang on. I'm just going to, if you don't mind, I'm just going to copy this. Oh, what is it doing? Okay. I'm going to copy that. Okay, so I'm going to copy this equation. And I'm going to take it down there because I want to see, I want to use the equation with these two numbers in it. Okay, let's see. So I'm going to put in these two numbers and see if this makes sense. First of all, that number on the left was, okay, I'm going to get it recalculated anyway. So I'm going to recalculate the number on the left. And, okay, it's not listening to me. Okay, so I'm going to calculate the number on the left right here. I'm going to write that down. So I'm going to do it with the calculator here real quick. Make sure 200, oh no, 20, and 20, divided by 2, divided by 32.2, plus 10. Uh-oh. Was that number 16.2111? Did I copy that down wrong? No, that's right. Okay, there it is. Okay. Okay, so we got that. Then I'm going to go in and equals to H, which was 11.576. 11.576. I'm just filling in. And what I'm doing is I'm just checking this. 17.277 squared over 2 times 32.2. Okay, so let's see. 17.277. And I got to square it. So divide by 2. And divide by 32.2. And I get 4.635 added to 11.576 plus 11.576, and I get 16.211. So in fact, believe it or not, that's the solution. Now, what's ironic is you can, okay, so here's what's happening. So if I drop this speed down to 10, what do you think will happen? And so what's happening now is there's a lot of energy, so it picks up here. But if I drop that speed down, what you'll find is it drops way low. And so, okay, this is weird because there's three things that have to be satisfied. The other is momentum. And so in other words, this could happen, but in order for it to happen, there has to be a lot of momentum resisting this. In other words, there's going to be a lot of force on this thing. More than likely, 20 foot, it can cause this, and there are cases where you can find that. You can find hydraulic jump and stuff like that. This is one of the weird things in fluids, is that in structures, you can use superposition. The reason you can use superposition is everything is kind of linear. In fluids, when you just look at that term right there, this right here causes you all sorts of havoc because it's a quadratic term. And in fluid mechanics, you can get some weird effects like that. And there's a lot of bizarre effects. For example, here's a bizarre effect. And I actually have this. I'd have to find it. Anyway, you take a spool of thread, or say you take, what we have is a 6-inch diameter piece of aluminum with an air hose connected to the top, and it's just a flat plate. And I mean, that's a cylinder. There's a hole all the way through it, and if you pump air through it, just air, what's going to happen is on the outside, it's going to lift this thing off the ground, right? And so from you're looking at it from the back side, you see a hole coming at you, you see air coming at you, and it's coming out this direction like this. So it's doing like this. So you're sitting there. This right here is the air coming at you, and it's going out like that. You turn that on. Your first inclination is that, let's say you put a piece of wood against it, and you turn that air on. Your first inclination it was to blow that wood off, but in fact it sucks it on there tighter. And so in fact you can take air pressure and blow through something, reach down, put it on this laptop, blow air onto the laptop, and pick the laptop up. And your first inclination is, that doesn't make sense. Until you realize that, okay, if you look at any one of these circles, concentric circles, what's happening is the area is going out. So the last point here, this has the slowest velocity. Up around in here, it has a really high velocity. So velocity is high. So if you write Bernoulli's between here and here, what you find, so this is near the inlet and this is near the exit, then what you find out, low velocity, I'll just call it V low, then V high, and this is all at the same elevation. So what you have is Pi plus rho Vi squared over 2 is equal to P exit plus rho V, oops, that's supposed to look like a V, V exit squared over 2. So this number right here is lower. This one is higher. This is atmospheric. And so gauge pressure, this would be 0. So let's just make up numbers. Let's say this is 2 and this is 10. So this has to be -8. So what you pull is a vacuum. And you're pulling a vacuum closer back in here. So this is a lower pressure. If you plot the pressure, now you'll have this spot where it comes out at, and it'll be blowing, have a high pressure, and then suddenly it'll drop like this and come up. So a majority of this lower pressure is over this larger area, and it will suck that. As a matter of fact, the first time I did this was in 2004, and we worked a problem like this, and one of the students was working in a shop, and they built this device. And they just didn't believe it. When they started doing it, the reason they built it is they had these big monster power or blow down tanks out there because they used pneumatics in their factory. And so in their break time, they built this device. I still have it of it. They started picking up big chunks of metal. So they had enough airflow through theirs that they could sit there and pick up the metal. The thing was, once you pick it up, if you tilt it over, it'll just slide off. It's just, there's nothing to keep it from staying on there. So it does actually work. There's a lot of weird effects that come out of fluids. This is one of them. This is rare. And this is my own fault. I should have made this a smaller number. If I'd have made that a smaller number, it would have came out to be a lot lower. But that's my fault. I gave it too much energy. Yeah. I should have made that 10. If you'd have made that 10, it would have changed a lot of stuff. And I really don't feel like going back through it. But if you do change it to 10, because then that, you think about it, that 20 is a lot of energy. And if you put that at 10, everything changes dramatically. I guess I could do it, but I don't know if I even want to. If you want to, I'll do it Monday after spring break. So the other thing you can do, and happens a lot, if you ever go, say you got a river flowing, right? and you want to know the speed, and you're like, well, what's the speed? If you have a boat, and you can actually do this, let's say you're out in the water and like you're on the White River, and you tie your boat or you put an anchor on there, because if you're fishing, a lot of times they'll throw an anchor on. If you're not moving very fast, you can actually take a drinking straw, although it would be something like a drinking straw. You dip it in the water, and what you find out is this is your velocity head. This is how you can tell how fast you're going. So if you write between 1 and 2, P1 plus gamma Z1 plus rho V1 squared over 2 is equal to P2 plus gamma Z2 plus rho V2 squared over 2. The water is stagnating against that. These are at the same elevation, so what you get is P1 plus rho V1 squared over 2 is equal to P2. But then you realize P2 is, it doesn't matter whatever distance this is. So let's just call this K, and let's call this H. So the pressure at P1 is K gamma, because you take that and you swim down to here, that's your pressure there. Rho V1 squared over 2 is equal to, what's P2? It's K gamma plus H gamma. The part that is your reading, the amount above the surface of the water. These two cancel, and so what you get is something that you might have seen before. Okay, wait a minute. V, because that's what you want. You want the velocity of the river is square root of 2 gamma H over rho, and gamma is rho times G, and believe it or not, it's just 2GH. So if you know G, and you read H, you can tell the velocity of the river just like that. Although most of the time the White River is going so fast that you need something larger than a drinking straw, but something like that, maybe I don't know, some sort of tube or something that turns 90 degrees so it can stagnate across that front end. This is a standard. People who work in parks and rec and some of the river flow stuff, they actually use this to figure out velocity of water. The other thing they do that I thought was interesting, and I didn't realize this, they would take a straw with ink and take photos on their iPhone, and they would watch the thing, and they would basically go back and look at the time on the iPhone, and they would back out the velocity that way. Which I don't know which one's easier. This one to me would be easier. With just a piece of elbow. I mean, you could take a small pipe. You could take a piece of PEX pipe and do that, but I'm not sure. You'd have to be able to see through the thing so you could see the water in here. Maybe I know there's clear PVC pipe. I know you can buy that. So.
You have to do or like if you had like a curved elbow.
Yeah, it'd be perfect if you just got something close to it. What you find out, and this is what's funny, is you could have that water coming at you, and you tilt it a little bit. You'll find out it's not terribly sensitive to it until you kind of get way far away from it. So if the water's coming at you, you could just sit there and play with it, and you could say, okay, the most I've got at 6 inches of water, and then you just go in and 6 inches of water is 32.2, a half, just 32.2, square root of 32.2. I don't know. So 6 inches of water would get you, I don't know what the square root of 32.2 is. Square root is 5.6 feet per second. So, that's probably pretty close to what the White River moves at, I don't know if you've ever been on that, but when it moves. I mean, it is moving. You can look down there. You know, where other places you'd see grass sitting like that, the grass there is leaning over on its side. It's just coming. I don't know why the grass down there grows like that, you know. So, but I'm not a grass person. I don't know. I'm not, you know, I'm barely an expert at fluids. So if y'all don't mind, we will just call it a day.